Okay, let's talk about, I'm going to keep talking about this example a little bit here. So this one, x equals cosine t, y equals sine 2 sine t and t. So first, how did we think about this? We thought about this as, right, so cosine t and sine 2t combined made an ellipse. So and as t increases, it circles around and sweeps out points on an ellipse. So can we write the equation of that ellipse? Do you know what the equation of ellipse is? So it's like a circle, but then it's like, right, so x squared, y squared, right, so remember, so that you have the divided by the radius squared in that direction. So this is kind of like x squared over 1 squared. So in the x direction it has a radius of 1. In the y direction it has a radius of 2. I could have written 2 squared here. And that equals 1. Okay? And then in x and z. And so then what do we say? We said, okay, and then x and z. What's the equation of x and z that we could write? X equals cosine of z, right? X equals cosine of z. Because if z is t, then when I'm just looking at x and z, I could make t equal to z, so cosine z. And then also, y equals 2 sine z. Okay, but in order to get the curve, we didn't really need that. We didn't really talk about that stuff. We just said, okay, right away we noticed cosine and sine are x and y, and we got this 2 here, so that's an ellipse. So imagine t increasing, and so without thinking about z, it's just gonna, as t increases, it's gonna sweep out points around that ellipse, right? But then as that's happening, what? Z equals t. So yeah, if t increases, then z is just going to increase with t. So then we just thought, oh, okay, so it's going to spiral around like an ellipse, but go up as it does that. So that was the way we thought about it Monday. But now a different way to think about it is the fact that we have 3 equations, each of 2 variables. And what do we say about if you have an equation of 2 variables in R3, what do we say that is? Cylinder, right? So what kind of cylinder is that? Elliptical cylinder. So if I come in here and I graph that elliptical cylinder, x squared plus y squared divided by 4 equals 1, what's going to happen? So how's that going to relate to our curve? What's that? Yeah, the curve is going to live on that elliptical cylinder. Let's make this thicker here. Why? Because that surface is going to have all those same xy ordered pairs. It's going to have more, but it's going to have all those xy ordered pairs. Okay, right? So there's that elliptical cylinder. Let's see, is this helpful? Let's try. Is this easier to see there? A little bit, yeah. Okay, well, what about x equals cosine z? If we just looked at that in space, what would that be? Right, is it another cylinder? Right, it's because one variable is missing. So in the xz direction, letting y be any value, you get a sinusoidal cylinder. So let's graph that one. X equals cosine z. The light color here. Let's try light green. I don't know if that's going to work. Let's see that. I'll turn this one off. Does it show up? Yeah. So look, so there's a sinusoidal cylinder, x equals cosine z. and the curve lives on that cylinder. And likewise, what y equals 2 sine z. So this is y equals 2 sine z. So it lives on that cylinder. So that curve lives on 3 cylinders. It lives on the cylinder you get when you combine the x and y. You combine the x and z and the y and z. But even more than that, it's going to be the intersection of all 3 of those cylinders. So what was the other one? X equals cosine z. So I don't know how well this is all going to show up here. So we'll make this, these are my 3 lightest colors. We'll make this dark blue, and supposed to be a radius choice there. I don't have a radius choice. Okay, let's see what happens. So if you enter, that's a pretty good view. So there, can you see the elliptical cylinder? If you take these 2 sinusoidal cylinders and cut them in at right angles of the elliptical cylinder, the intersection of all 3 of those surfaces will be your curve, the blue curve. Let's make it red. There, now we got radius. So this is kind of extending the idea of the projection into the planes, right? We said if you combine 2 variables for that curve, it's what you get projected into the plane. Well, now if you think about those as surfaces, then it's the intersection of the actual curve becomes the intersection of the surfaces. Maybe that shows it better. Does that show good? Yeah, that shows it pretty good. Okay, so that's what we want to talk about. So if you have 2 surfaces and you intersect them, you're going to get a curve in space. So based on those equations of those surfaces, we should be able to come up with a parametric equation of the curve, right? Or the vector function for the curve. So that's what we're going to talk about. Okay, so gave it all away here. Let's turn this off. What's it? And then you actually have a homework question like that. So there's a homework question that says, write the parametric equation of a sphere. That's the intersection of a curve that's the intersection of the plane and the sphere. So I'll just make up a similar example. So let's just actually do a lower problem. This one. Is it? No, different one. Next one. Okay, so you have this sphere. X squared plus y squared plus z squared equals 53. So that's centered at the origin. Something like this. Okay. And then the plane y equals 2. So then y equals 2 is going to come along here. And so when you intersect that plane y equals 2, a vertical plane through that sphere, what will you get? What will be the result? Yeah, if you slice a plane through a sphere, that should make sense that you're going to get a circle. So something like this. Like that. Show it very well. Red. Okay, so how are we going to get the equation of that circle? So this is the idea that ends up being the intersection of two surfaces. So what are our surfaces? Y equals 2 and x squared plus y squared plus z squared equals 53. So we want the intersection of those two surfaces, or all points that lie on both. So we're going to bring the equations together. So how do we bring the equations together? Yeah, you're going to plug your y equals 2 in for y. So you want the points on this sphere such that y equals 2. That's what that means. So then we get x squared plus z squared equals 49. And so now if we want to write that, we know that's our circle. We want to write it parametrically. So what do we know now about the x, y, and z coordinates? What's true about every point on that circle? Y is 2, right? That circle lives on y equals 2, so every coordinate is 2. And then we've got x squared plus z squared equals 49. Radius is 7. And what's the natural way to parameterize a circle with two variables? Cosine and sine. Cosine and sine. Don't solve for one variable, then you get square roots and plus or minus, and it's not natural, right? The natural way to parameterize a circle or ellipse is cosine and sine. So when you intersect surfaces, you get a curve, and so based on those equations of those surfaces, you should be able to write the parametric equation of the curve. All right, does it make sense? Or the vector equation, I should say, vector equation. All right, so let's do another example of this. Let's look at this. Z equals x squared plus y squared. And z equals 1 plus, that's not what I want. I think I want z equals 1 plus y to start with here. That's what I want to start. Z equals x squared plus y squared, and z equals 1 plus y. So can you sketch those individually and try to imagine what the curve of intersection will be before we do any of the math? Can you sketch those individually? So what's our repertoire of surfaces here? Spheres, right? Ellipsoids. Cylinders. Planes. A couple more. Paraboloids. Is there another one we got? We're not going to really do hyperboloids. It's too many, I think. I feel like there's one more. Double cone. Thank you. I knew there was one more. So these are what we made right around the time of exam 1. So on the next exam, there's a big portion of the test devoted to seeing if you know these. Okay? Because they're going to come back all course long, so you got to know these back and forth from their equation, right? Given the equation, could you sketch it? Could you tell its qualities as a graph, and could you sketch it? Given a graph of a surface, can you identify its qualities and then write the equation? So there's like I said, big chunk of exam 2 is about knowing your way in and out of these. The visual and the equation. Okay, so we come to here. Do these fit the bill of our known surfaces here? Z equals square root of x squared plus y squared. Is that one of the ones? Is that one of these? Or does it come from one of these?
Yes.
Answer is yes. Do you remember? What would that be? Nick knows. Double cone, right? Because if you squared both sides, you get z squared equals x squared plus y squared. But what's going on here? Key? You look like you're going to say something, Key. No? What's different about this from, is it a double cone?
Looks like half.
Yeah, why half?
Because z can't be negative.
Right, when you square root both sides, if you have a plus or minus, then you get everything you had before. But if you just take the plus, you're just taking the values of z that are positive, right? So we're just going to get maybe something. It'll just be the single cone for positive z. Okay, so we got the single cone. All right, what about z equals 1 plus y? Yeah, it's like a cylinder. It's like what kind of cylinder is that? Z equals 1 plus. If you want to call it a cylinder, you could, but then you'd say, what kind of cylinder is it? What? Linear cylinder, right? It's like you're taking a line and extending it. Well, what is that? That's a plane, right? So this is like, so yes, you can think of this as a linear cylinder, right? Because it only has z and y, so you just extend it in x. Or you can think of it as 0x minus y plus z equals 1, our equation of a plane. Both are valid. So when you intersect the cylinder z equals 1 plus y with this cone, what will you get? Is there a question?
Yeah, could you just explain why it's a single cone again?
Because a double cone was z squared equals x squared plus y squared. And why was it a double cone? Because we could put negative values of z in here and still have a valid result because you square the z. But now if I take the square root of both sides and I want to recreate this whole thing, what do I need? Plus or minus. So that's saying z could be positive values because the square root's always positive. So when you take plus, you get positive. When you take the minus, you get negatives. So the minus would be the bottom cone for all the negative z values. Better? Cool. All right. What is, when we take this plane z equals y plus 1 and intersect it, what do you think we're going to get? What would you get for a constant z value? Constant z. Constant z? Like pick a constant z value. I'm asking you about the intersection of those two surfaces. What will it be? Circle, right? The trace will be a circle, right? So now I'm thinking z equals 1 plus y. What might that be? Okay, it's slanted now, right? So ellipse. Let's find out. Okay, so let's do the math, and then we'll find out, and then we'll graph it and see. Okay, so I want to find the curve of intersection. So I want to bring these equations together. How can I? So this one's kind of pretty easy first step. How can I bring those together? Yeah, so just since they're both equal to z, I could just set them equal to each other. And then for both sides. That's FOIL, right? There's 3 terms, not 2. It's not 1 plus y squared. It's actually, these go away. Okay. I can solve for y. So y equals x squared minus 1 all over 2. So what is this? This is like if we were, this is what we would see looking down on the intersection of these two surfaces, right? We've got these two surfaces, the plane and the cone. If we were to look down on it, take z out of the picture, we would get what? Parabola. Okay. Now what can we say? How can we so we're thinking about writing this as a vector function, right? And so now I've got z equals 1 plus y, and y equals the square root of x squared minus 1, or x squared minus 1 over 2. So how might I parameterize this? What might I do? Parameterize this and get my x, y, and z. So do you notice I could just, so if z is 1 plus y, then z is 1 plus that. So what can I do to parameterize this? Do I want to use cosine and sine? There's no circle, right? There's no circle. I've got z equals 1 plus y. It's my z and y together. Y equals x squared minus 1 is my y and x. And then I could also, as like I said, I could write z equals what? 1 plus that. So there's no, do you see there's no, in terms of this, the intersection of these two? Why is that not? In terms of the intersection of these two surfaces, I've got my three equations of two variables. None of them have to do with a circle, so I'm not going to use cosine and sine. So instead, what's the another technique I can use? And what should I let equal to t? I should let x equal to t. Because then y is just simply t squared minus 1 over 2. And I think if you do the math here, you get, ends up being x squared plus 1 over 2. So t squared plus 1 over 2. So what are we going to get? Let's see if that's what we got. Yep, there it is. I had that from before. So let's make that yellow. And we'll make this, let's see if do blue and red show up good together. Pretty good. So now look, so there's the two surfaces, right? So you got the plane and the cone. And what do you see? The intersection. It's parabolic, right? So if I turn on the curve that we found, it should go right along that crease, or right along that intersection. So that's what we said, right? T squared minus 1 over 2. So I'm going to turn it on. There it is. A little bit bigger. Okay, so that would be if I were to what? So if I turned off that cone and graphed the three equations of two variables, right? I got z equals 1 plus y. What else? Z equals x squared plus 1 over 2. That's another parabolic cylinder. So I got the plane, the one parabolic cylinder, and the other parabolic cylinder, which is which one? Y equals x squared minus 1 over 2. So that yellow curve we found is the intersection of those three, the plane and the two parabolic cylinders. Does it show up on the screen? If it's any better. Yeah. Should have done yellow here. Should have done. Anyway, so does that make sense? Okay. So how would you get then? Why is this a parabola when you guys were saying we should get a? We should have gotten a ellipse. So what's going on with that? Why? So those are the two original surfaces, intersected them, and we got a parabola. But an ellipse was a good thought, but we got a parabola instead. Why? What would make it an ellipse?
If it had a lower slope, it would intersect both sides.
Right. So this plane has the same angle as the cone. That's why we're getting a parabola. See that? See that angle of inclination of the plane is the same as the side of the. It's like a 1-to-1 ratio, right? The slope of 1. So if we change the angle of that plane, say make it 1/2 y, I'll turn that off. Then what do we have? So yep, so it's an ellipse. The intersection is an ellipse. So we're going to find that intersection. So this is a different. So now how will our parameterization of this ellipse be different than parabola in space? Yeah, so we're going to expect sine and cosine now, right? Because that ellipse is going to be based on sine and cosine. So here we go. Let's do it. So we're going to start with the same first step. We're going to set the two equal. So this is a new problem now. A new problem with a new plane that gives an ellipse instead of a parabola, right? So we're going to start with 1 plus 1/2 y equals. So what's going to happen now is that the y squared isn't going to cancel out nicely like it did before. So we got 1 plus 1/2 y squared. Squared plus y squared. And then we're going to FOIL out the left side. So 1 plus 1/4 y. Nope. Just y. Right, 2 times 1 times 1/2 y. Plus. Okay, so now the y squares don't go away the way they nicely did last time. So what are we going to do with this? So remember what our equation of ellipse is. It's going to be x minus a squared over some r radius squared plus that's our general equation of an ellipse. So we're moving towards that. We want to move towards that. So we're going to gather all the terms on the left side. And I want these to be positive. So I'm going to move everything to the right and then just switch sides. Is that okay? So just move everything to the right and switch sides. So I have x squared over here. And then plus y squared. Oh, actually, what I'm going to have 3/4 y squared minus y. And that's all going to equal 1. Did I do the math right? Okay, so what do we need? We need to complete the square. So to get the ellipse form, we need to complete the square on y. So in order to complete the square, I need a coefficient of 1 on y squared. So I'm going to factor the 3/4 out. And when I factor 3/4 out of 1, I'm left with What times 3/4 gives 1? 4/3. Did you catch it? So now I factored 3/4 out of both y squared and minus y. So if I were to multiply that 3/4 back in, I'd have what I had before, 3/4 y squared minus 1y. Are we good? And now inside the parentheses, we'll complete the square. Remember how to complete the square. Yeah, you're going to take the linear coefficient, square it, and divide by 2. So, what is that? 16/9 or 16/18. Okay, so if you think we're making an error, please speak up. We don't want to get through. We got a lot more steps. If we dig a hole for ourselves, that's not good. So are we? This is again 16/9 divided by 2 is that 16/18. Yeah, of course you do. Thank you. Divide by 2 and then square. I knew that didn't feel right to me. So 4/6 is 2/3 square. 4/9. So yeah, you take the linear term, you divide by 2, which is 4/6, or 2/3 squared is 4/9.
Yeah.
Okay, that if we did it right, we got a perfect square there. And what's the perfect square? Yes, but actually we're not adding 4/9, but we're adding what? 3/4 times 4/9, because we added 4/9 inside the parentheses. That comes then with the 3/4. So are we adding 1/3? Good thing you guys are here. Okay, x squared, so we got x squared plus. So y minus what? 2/3? Quantity squared equals, oh, and that's going to be over, I'll put that over 4/3. And that equals 4/3. Okay, check that. Let's pause there and make sure we're right. Which one? I did 1/3 to both sides, so 3/3 plus 1/3 is 4/3, right?
Yeah.
What's that? No, I added 4/9 inside the parentheses.
Yeah, that's both sides.
And so that's really adding what, 3/4 times 4/9. So you got to add as both sides to keep the balance. So are we good on the right side?
Yeah.
Okay, now this. So this used to be multiplied by 3/4, and that's the same as dividing by 4/3. So that's the 4/3 is this one, reciprocal in the denominator. Are we still good? So what is that squared? So 1 minus 2/3 squared, what's squared? 2 over radical 3. And what is this squared? 2 over radical 3. So I think we've got our ellipse now. Or elliptical cylinder, right? This is going to be an elliptical cylinder that goes up and down because there's no z in there. So what's the center of the ellipse? Zero and 2/3. The x radius is 1. The y radius is 2 over radical 3. Oh, this isn't right. We got to get a 1 over here. A little bit. We got to get a 1 on the right. So now we have to. The last step is, how do we get a 1 over here? We're going to divide both sides by that. So it's going to be. It's actually the x radius is going to be that. So it's x over. think this turns out to be 4/3 squared. Yep. There we go. Now we're and that's equal to 1. Now we're ready to analyze the ellipse. Okay, so x, let's see, x radius is? So radical 3. Y radius is? 4/3. And center. That we had right. And now we have to parameterize that. So with this information, the x radius is 2/3, y radius is 4/3, and the center is 2/3. How do we parameterize that? How do we get that in sine and cosine? So what is the key? What's the key that links this to sine and cosine? Yeah. Well, yeah, so we're working towards the equation. So what is the key that links us from here to sine and cosine? Yeah, exactly. The Pythagorean identity, right? The Pythagorean identity. So the Pythagorean identity says that sine t squared plus cosine t squared equals 1. So we've got that. We've got something squared, right? Plus something squared equals 1. So that something that's squared, we can assign that to sine t. So we can say sine t equals what's squared here? X over 2 over square root of 3. And therefore x equals? And then we can assign what's squared here, we can assign that to cosine t. So we can say cosine t equals, do this now. So from this we said that x equals 2 over radical 3 sine t. And we could use cosine t there and sine t here. It'll just give a different way that the ellipse is generated, just in terms of direction and starting point, but you get the same ellipse. All right, and then in this case we're going to get so cosine t equals y minus 2/3 over 4/3. So then y equals 4/3 cosine t plus 2/3. Okay, and then how will we get z? So look, we're starting to form the vector function for the curve, right? We got the y in terms of t, x in terms of t, and then how would we get z? Where will z come from? Where will z come from now? How will we get the z for the parametric equation? Or the vector function? What does z equal?
1 plus y, 1/2.
Yeah, we're going to use this, right? So 1 plus 1/2 of y. We know what y is, right? So z is going to be 1 plus 1/2 of that. And then we got our x is a function of t, y is a function of t, z is a function of t. Moment of truth, right? The moment of truth. Did we do it right? So I think, let's see if that's what we got last semester. That was for the parabola. So 4/3. Let's just put in ours. Okay, so we'll put in ours. So maybe more than one way to slice this. So we'll put in ours and make sure it's right. So we want what? Oh, please be right. Okay, and then 4/3 cosine t. And then 1 plus 1/2 of that. What happened? Sure. I'm already halfway there, so I'm just going to do this one. Symbolic, right? I'm taking the y and I'm putting in the parentheses. But that just might take me a while. Got it. So delete and paste. Is this what we did? Here we go. Better be right. Make it yellow. Should be giving me a radius. Not yet. Here we go. We did it. So this time we knew that it was circular or elliptical, so we knew we were going to pick cosine and sine. And then the way you do that is you get your equation of your ellipse or your circle to look like cosine squared plus sine squared equals 1. And then you can pull off that thing squared and set it to one either cosine or sine. Pull off the other thing, whatever it's squared, set it to the other, and then solve for your x and y. And then z came from the original equation, the 1 plus 1/2 y. Up here. And then again, this is going to be the intersection of looking at our vector function, this one, there's 3 cylinders, right? So the x and y is this cylinder here, right? So this cylinder right here is combining those two, the x and y, you would get this elliptical cylinder that runs up and down parallel to the z-axis. There it is right there. Center, what, 0, 2/3, and then the radii that we found. Then what will you get in this direction? In the yz plane? We're still talking about that linear cylinder or the plane. And then what if we were to combine x and z, what would we expect? Does it still show up? So if we were to combine the x and z components of that vector function, another ellipse, right? You see it? Really? There we go. So you get another moving on me. Don't move. You get another elliptical cylinder running down parallel to y. If we were to combine the x and z and figure that out, we could get the equation of an ellipse, and that would be that elliptical cylinder. All right, try this one. Got 5 minutes. 2 plus 1 is 3. Should be 3. What is that?
7/4.
7/4. Does that answer it? Yeah.
I guess when we get to it, I was just confused with the third line to the fourth line.
Here to here?
Yeah.
Completing the square. So I got to complete the square. And to complete the square, you take half of the linear coefficient and square it.
Okay.
So half of 1 is 1/2. Squared is 1/4. I'm going to add 1/4 to both sides.
Okay.
And that completes my square. So what is this now? What is that? Ellipse? Circle. So this one's a little bit easier to parameterize. I can just say x equals cosine t. Oh, I can't do that. Gotta divide by 7/4. If I'm going to use the sine squared plus cosine squared equals 1, I've got to get a 1 on the right before I can do that. Now I'm ready to say that could be cosine t, and that could be sine t, and solve for x and y. Is that 7/2? Let's square the whole thing. Right. And then z again I can get from the 2 minus 2y, plugging in this for y. Let's see what it looks like. So that's a plane cutting through a paraboloid and another ellipse. But I need to get the z too. So here's my x for my vector equation of the ellipse. I got the x, the y, and the z can come from the 2 minus 2y. Yep.
Is it an ellipse or a circle?
Okay, so good question. Is it an ellipse or a circle? Yes. Because it's truly slanted in space, it's an ellipse. But in x and y, just looking at x and y, it's a circle. Right? Just in x and y, it's a circle. But when you bring the z into it and it's slanted in space, it's an ellipse. Great question. Right? And that's backed up by what happened, right? Because the x and y equation was a circle. So that's, if you take z out of the picture, there's the circle. Okay, yes, recitation tomorrow. No written homework tonight, but yes, recitation tomorrow.